or billions of years. A star maintains a balance between gravity trying to compress it and the pressure of thermonuclear reactions trying to expand it. But when the fuel runs out, this balance is disrupted. The outer layers of the star explode in a catastrophic flash called a supernova, one of the brightest events in the universe. And the star's core collapses under the action of its own gravity. It compresses more and more until it reaches such density that even atoms are destroyed. Matter continues to compress until what physicists call a singularity is formed, a point in space-time where density becomes infinite. Imagine an object that compresses mass exceeding the mass of our sun into a space the size of a city or even smaller. Some black holes have a mass of tens of suns compressed into an area of just a few kilometers. The density of such an object simply defies imagination. If you took a teaspoon of matter from a black hole, it would weigh billions of tons. Around the singularity exists an invisible boundary that scientists call the event horizon. This is the point of no return, the final boundary. Once anything, whether a spaceship, a photon of light, or even information, crosses the event horizon, it is doomed to fall into the singularity. No force in the universe, no technology, no laws of physics can save an object that has crossed this boundary. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of our sun, the radius of the event horizon would be only about 3 kilometers. This is called the Schwarzschild radius, named after the German physicist who first calculated this value. There are different types of black holes, and this is important for our scenario. Stellar black holes are formed from collapsing stars and have a mass from 3 to several tens of solar masses. These are the most common black holes in our galaxy, and there may be millions of them. Then there are supermassive black holes, which are located in the centers of virtually all large galaxies, including our Milky Way. These giants can be millions or even billions of times more massive than the Sun. The black hole at the center of our galaxy, known as Sagittarius A-, has a mass of about 4 million suns. There are also intermediate black holes with masses from hundreds to thousands of solar masses, although they are rarer and less well studied. And finally, there are theoretical primordial black holes that could have formed in the first moments after the Big Bang from density fluctuations of matter. For our scenario, let's consider a stellar black hole with a mass of about 10 solar masses, a fairly typical representative of its class. This is a medium-sized black hole, not too small and not gigantic. Its event horizon would have a radius of about 30 kilometers. It's important to understand that black holes don't suck in everything around them like a cosmic vacuum cleaner. At large distances, their gravity acts exactly the same as the gravity of any other object of the same mass. If our sun suddenly turned into a black hole of the same mass, which, by the way, cannot happen since the sun is not massive enough, Earth's orbit would not change. We would continue to revolve around it at the same distance. The danger of black holes manifests when you find yourself too close to them. That's where gravitational effects become extreme and truly strange things begin to happen. Now that we understand the nature of our adversary, let's see what will happen when Earth begins its fateful journey to this cosmic predator. So, let's imagine an incredible scenario. Somehow, perhaps due to gravitational disturbance from a passing star or some other cosmic cataclysm, our Earth was knocked out of its comfortable orbit around the Sun. It began to drift in space, and its trajectory, by unfortunate coincidence, leads directly to a black hole. When will we first realize we're in danger? When would the first signs appear that something terrible is approaching? Assuming Earth began movement from the periphery of our solar system in the direction of a black hole located at a distance of several light years, the first signs would appear long before we approached the black hole itself. Astronomers would be the first to sound the alarm. Black holes themselves are invisible. They don't emit light, but they manifest themselves through their gravitational influence on surrounding space. The first alarming signal would be a change in the starry sky. Astronomers would notice a strange region of space where stars behave unusually. Their light is distorted. They change position or disappear. This phenomenon is called gravitational lensing. A massive object, such as a black hole, curves space-time around itself, and this curvature bends the trajectories of light rays passing nearby. As a result, we see distorted, multiple, or magnified images of distant stars and galaxies. As Earth continued its movement, this strange region of space would become larger and more noticeable. At the center, an absolutely black area would form, the shadow of the black hole. Around it, we would see a ring of light formed by photons orbiting the black hole. This phenomenon was first photographed by astronomers in 2019 when the first real image of a black hole in galaxy M87 was obtained. But visual effects would be the least of our problems. As we approached, at a distance of approximately several million kilometers from the black hole, its gravitational influence would begin to become physically tangible. The first victim would be our moon. The moon is held in orbit around Earth thanks to a delicate balance between Earth's gravity and the centrifugal force of its orbital motion. But when an external force, the gravity of the black hole, began to interfere with this balance, the moon's orbit would become destabilized. At first, the changes would be small. The moon would begin to move along a slightly different trajectory. Its orbit would become more elliptical. But as the gravitational influence of the black hole strengthened, the moon could either move away from Earth or, conversely, begin to approach us. In the worst case, it could be completely torn from orbit and sent on its own journey to the black hole. What's interesting is that these effects are related to so-called tidal forces. Tidal forces are the difference in gravitational attraction between the near and far sides of an object. On Earth, we observe tides in the oceans precisely because of the tidal forces of the moon and Sunday. But the tidal forces of a black hole would be on a completely different level. At a distance of several million kilometers from the black hole, these forces would begin to affect Earth. The side of the planet facing the black hole would experience stronger gravitational attraction than the opposite side. This would create tension, tending to stretch the planet along a line directed toward the black hole. On Earth, we would begin to observe strange and disturbing phenomena. Ocean tides would become extreme and unpredictable. Normally, tides caused by the moon and sun raise the water level by several meters. But now the black hole would add its contribution, creating tidal waves of unprecedented force. Coastal cities would be under threat. Water would rise tens of meters, flooding low-lying areas. But these would not be ordinary tides that predictably come and go. The gravitational influence of the black hole would create chaotic, unpredictable changes in water level. Navigation systems would begin to malfunction. Modern civilization relies on GPS satellites that use extremely precise calculations based on general relativity. These satellites account for the fact that time flows slightly slower in the stronger gravitational field on Earth's surface compared to satellite orbit. But the presence of the black hole would introduce additional gravitational distortions that were not accounted for in the algorithms. GPS coordinates would begin to drift and become unreliable. Communication with spacecraft would become difficult. Radio signals that we send to our probes and receive from them propagate in straight lines through space. But the curvature of space-time around the black hole would bend the trajectories of these signals, causing delays, distortions, and loss of communication. Astronomers would observe increasingly dramatic effects in the sky. Stars would begin to move from their familiar positions due to gravitational lensing. Entire constellations would be distorted beyond recognition. The black hole would dominate the sky, a huge dark area surrounded by a distorted, pulsating ring of light. But all this would be only a prelude. The real nightmare would begin when we approached even closer to the black hole. Let's continue our journey into the abyss. Now let's imagine that Earth is at a distance of about 1 million kilometers from the black hole. To understand the scale, this is approximately 2.5 times greater